Hi viewers, welcome to LMS Solution. Today we are going to see about three-phase grid connected solar PV and the battery system. Thanks for watching your videos. Kindly subscribe the channel and also click bell icon for notification about upcoming videos. So this is a model is developed for testing the three-phase grid connected solar PV and battery systems. So this model consists of the solar PV system and battery storage systems, and then three-phase inverter is connected with the grid. So here the PV panel we are having, that means we are connecting the 250 watts and 250 watts panel in series. The series string having 15 model, and then there are two parallel strings. For single panel voltage rating is around 30.7 at maximum power point condition and 8.15 amps at the maximum power point condition. And this is the IV and PV characteristics of the considered PV array. That means 15 series string and 2 parallel string model. The maximum power for the different irradiation condition you can see here, right? For 1000 watts per meter square, the maximum power is around 7506 watts, and voltage at maximum power point is 460.5 volt. So we can see the maximum power for the different irradiation condition. Okay. So next process, here we are going to connect the solar PV to the DC bus. So this is going to be considered as a DC bus. The three-phase grid connected solar PV and battery systems. So we need to design this boost converter, because boost converter is connected between solar PV and the DC bus as well as DC load. Okay. So we need to design this boost converter. So in order to design this boost converter, so we need to fix the input voltage. So here I'm going to fix the input voltage is 460.5. That means I'm going to consider voltage at the standard test condition, and the power at the standard test condition is around 7500. Okay. And then you have to fix the output voltage here. So not to fix the output voltage, so we need the grid voltage, grid line to line voltage. So here I'm going to consider the grid line to line voltage is 400 volt. So if the grid line to line voltage is 400, then we need to select the DC bus voltage in between 1.5 to 2 times of the line to line voltage. Okay. So that means 1.5 into 400, 2 into 400. So we can choose the DC bus voltage around 600 to 800. Okay. But here I'm going to take the average of these two value. So 600 plus 800 divided by 2. So that is equal to 700. So I'm going to select the DC bus voltage is 700. So based upon this power rating of PV and voltage of the solar PV, the output voltage of DC bus, that means DC bus voltage 700. So you have to design the value of the LNC. Okay. So in order to design that LNC value, so we have the equation. So in the equation, we have to provide the detail about the PV panel voltage. So here we are consider the PV panel voltage is 460.5, and then we need to provide the switching frequency. So switching frequency here we are going to consider 10 kilohertz, and output voltage or DC bus voltage. So DC bus voltage is 700, and then you have to calculate the output current maximum. So that when we calculated based upon that single panel rating with the series parallel string combination 250 into 15 into 2. So you have to calculate the side out max, and then this equation is to for fixing the percentage to full inductor current percentage, and then this is used to for fixing the capacitor voltage, ripple capacitor voltage percentage. So based upon this value, you have to calculate LNC. So this is the equation used for calculating LNC. So I am going to simulate this one. So these are the values for that boost converter. That means inductor and capacitor value. So this value going to be used in the system. Well, and C. So same value of C, then when we are going to use in the input filter also. So input capacitor also. And next you have to design this bidirectional converter. The battery going to be connected to the bidirectional converter. So why we are connecting that battery via bidirectional converter means, so battery it going to be act as a source as well as store. So based upon power availability at the PV, okay, and sharing of power from the grid, okay. So battery can be at a zero sources plus load. So we have to design this bidirectional converter also. So here we are using that battery rating is 12 to 35. So that means we are connecting a 35 battery in series, 12 load battery rating rated battery is connected in series with the 35 model, and rating of the battery is 48 Ah. And here we are using lithium ion battery. So here we are going to design this value of LNC on the bidirectional converter. So for that I'm going to take the voltages 12 into 35, and then power rating I'm going to consider the same rating of the PV. The voltage in the DC bus is 700. So these are the parameter we are going to use to design that LNC of the bidirectional converter. So here you have to feed the voltage of the battery. Switching frequency, I'm going to consider the same switching frequency used for the boost converter design, and then DC bus voltage, and then the calculation will be, and then my IOT max will be calculated based upon the PV panel rating. So the remaining equation is same. That means the bidirectional converter acts as a boost converter concept, but the current direction going to be is forward or reverse. So it depends upon the power balance in the system. So I'm going to simulate this model. After simulating this program, so this is the LNC value for the bidirectional converter. So that value is used here. Okay. So next we are going to connect the system to the grid. Okay. So this is a three-phase inverter is connected via LC filter to the three-phase source. Okay. So we need to design this LNC value in order to get the proper waveform for voltage and current. That means sinusoidal voltage for the sinusoidal voltage of the sinusoidal waveform for the voltage and current. So you have to design this value. So this value going to be designed based upon this value. That means, so I'm going to consider the power rating for that LCL filter is 8000. So that means I'm going to take the power rating is more than that solar PV, slightly more than. So actual power rating of the solar PV is 1500. So here I'm going to consider 8000, and DC link voltage is 700. So here we are calculating the load current, and then here I'm going to consider switching frequency is 7500. So this is inductor ripple current. So here I'm going to consider 2% of the total current of the system, and then this is a formula used for calculating efficiency for that particular filter. So here I'm going to simulate this model. So this is LNC value for that AC filter. So this value will be used here, LNC. Okay. So if you say three-phase source, here you are having 400 volt line to line 50 hertz, and here you are using three-phase load. So load power is around 2 kilowatt, and then line to line voltage is 450. Okay, and this three-phase inverter will be controlled by means of current control algorithm. See, not apply current control algorithm. Here we are using a transformation, right? Like ABC to DQ transformation. So for that, we are going to measure the voltage across that capacitor, and also we are measuring the current through that inductor. Okay. So this voltage across the capacitor, so used to for generating the sine and cosine wave. Okay. That means, so by using PLL concept, so here we are going to apply PLL concept. So by using the PLL concept, we are generating the sine and cosine waveform. Okay, and this is known as current control algorithm for the three-phase inverter. So here you can see that we are measuring the inductor current of the that inverter. Okay, and here we are applying some logic. So that logic nothing but that means we are going to measure the PV current and associate the battery. So based upon the PV current associate the battery, we are fixing the current. So whether we are going to send the power to the grid or we are getting power from the grid. So that logic is implemented here. So here you can see that if IPV is less than 0.5 and SOC is less than 10, So I reference here we are fixing is 10. That means you are getting the power from the grid. Okay. So here we are getting the power from the grid. So this is known as we are sending the power to the grid. Okay. So this condition, if IPV and SOC is less than 0.510, then we are getting power from the grid. If IPV and SOC is greater than 0.510, then we are sending power to the grid with the reference current of -3. So that means 10 means 10. So divided by SURT 2 was around 7 amps. So 7 into 230 into 3. So totally we are taking power from the grid around 4830 watts. Okay, when the IPV and the SOC is less than 0.5 and 10 percentage. Okay, so when consider if suppose we are sending 3 amps, so 3 divided by SQ or T of 2. So this is around 2.12 amps, 2.12 into 230 into 3. So that means we are sending around 1460 watts to the grid when the IP is greater than 0.5 and SOC is greater than 10 percentage. So this is the power calculation for sending and receiving the power from the grid. Okay. That means so this is sending power. So this is receiving power depends upon the IPV, that then PV current and the SOC of the battery. So here we are, that means this is known as I reference is generated from the logic. So this is going to act as a D reference, right? Direct axis reference. So here we are converting actual current IA, IB, AC into DQ. Okay. So here after converting actual ABC into DQ, so it's going to be compared with the D reference. So the D reference is generated based upon the control logic, based upon IPV at SOC. And here we are making Q reference equal to 0. That means here we are only sending the real power, real and the real power going to were going to send to the grid or receiving from the grid. Okay, so that's why we are making MQ reference equal to 0. So and then it's going to be processed by the PI control. Okay, so this PI controller will be generate the controlled voltage, the form of TQ, so that DQ going to be transformed into ABC by using DQ to ABC. Okay, so based upon this modulation index M1, M2, M3, so we are generating pulse. Okay, so here we are applying the BWM generator. So this pulse is going to be controlled the 3-phase inverter. Okay, so here we are using 3-BWM generator. So this will be generate the pulse for the 3-phase inverter. So based upon this current reference, this inverter will be take the power from the solar PV battery system to load as well as a grid. If suppose IPV SOC is less than 0.5 and less than 10 percentage, then grid going to be supply the out to the solar PV system. Okay, to charge the battery and to supply the DC load. So this is all working up this operation of the 3-phase inverter for the grid integration. So and also here we are using incremental conductance MPPT. So this incremental conductance MPPT, you have to measure the PV voltage and PV current, and it going to be processed by INC. So here we are going to fix the initial duty cycle, maximum duty cycle, minimum duty cycle, but then you have to fix the previous voltage, power, duty cycle, current, and then you have to check whether it is empty or not, previous voltage is empty or not. If it is empty, you have to fix the voltage, previous voltage, power, current equal to 0, and then previous duty cycle equal to initial duty cycle, and then you have to calculate power of the PV, and then you have to calculate change in voltage, change in power, change in current, and then here only we are applying that incremental conductance in BPT concept. That means here we are comparing that the change in voltage equal to 0 or not. If change in voltage equal to 0, then you have to check the change in current equal to 0 or not. The both condition is true. That means already that PV operated to maximum power point condition. Then you have to maintain the current duty cycle which is equal to old duty cycle. If suppose this condition is not true, we are going to check the change in current is greater than 0. If change in current is greater than 0, then we have to decrement the duty cycle. If change in current is less than 0, we got to increment the duty cycle in order to bring that PV panel at a maximum power point position. If suppose this change in voltage is not equal to 0, then you have to check this condition. So this is nothing but incremental conductance condition. So di by dv equal to minus I by v, which is equal to I by b minus I by b. This condition true. So again, that PV operate at the maximum power point condition, then we have to maintain at that means we have to fix the duty cycle which is equal to previous duty cycle. If suppose this condition not true, then you have to check this condition. Di by dv is greater than minus I by v. This condition true, then you have to increment the duty cycle or incremental duty cycle. So after finding the duty cycle, you have to check the duty cycle value is that means greater than maximum duty cycle value or less than minimum duty cycle value. So this condition is satisfied, then you have to maintain the duty cycle with the duty cycle. Otherwise, you have to use that duty cycle calculation value, right? So this duty cycle when be given to that particular generator of the boost converter, you have to extract the maximum power from the PV panel. After that, every iteration you have to override the old duty cycle. That means V volt, T volt, I volt. So this when we keep on executing, you have to get the maximum power from the PV panel. So here you can see that. So it going to be provide the duty cycle, and then going to be process here particular generator. So it will generate the pulse. So this pulse going to be control this IGBT in order to extract the maximum power from the PV panel. Next here we have that bidirectional DC-DC converter. So this converter when we control like voltage controller, that means we are going to measure the DC bus voltage that when we compare with reference voltage, because here we are going to maintain the DC bus voltage at 700. So we are going to compare the DC bus voltage to 700 and it when we process a PA controller, this PA controller will be generate the duty cycle. So the duty cycle when we process a PWM generator, you have to generate the pulse. So this pulse will be given to these two IGBT in order to maintain the DC bus voltage around 700. Okay, so these are the control logic for a solar PV MPPT and voltage control of the bidirectional DC-DC converter. So next we have to check the results. So here I am going to fix the DC load power. Okay, so here the DC voltage is 700. So divided by the power rating. Here I am going to fix the power of the DC load is 1500. Or else we can take the power of the DC load is 2500. Okay, so here the DC load is 2500. So here the AC load is 2 kilowatt, right? And then here we are changing the irradiation for every 0.3 second from 1 to 0.5. That means 1000 to 500, and then 10 again is increased to 500 and then 1000 for every 0.3 second. And initially I'm going to fix the battery SOC is 50%, and then you have to check the results. That means so this will be used for measuring the EV voltage, current and power. So this will be used for measuring the DC bus, that means DC bus voltage and DC load current and DC load power. And this is used for measuring the battery voltage and battery current. So this is used for measuring the SOC of the battery. And so this is going to be used for measuring the grid voltage, inverter current, grid current. So this is used for measuring the AC load voltage current, and this is used for measuring the grid power, load power and inverter power. Okay, so the red color known as grid power, the pink color known as load power, the blue color known as inverter power. Okay, so now I'm going to simulate this model. Okay, and then I'm going to explain the results. So here the SOC of the battery is fixed at 50%, and then here we are varying the irradiation from 1000 watts per meter square to 500 watts per meter square, and then 10 watts per meter square. Again it will be increased to 500 and 1000 watts per meter square. So the changes will be every 0.33 seconds, right? So every 0.3 seconds, the status of the irradiation will be changed, and you have to check the results. So here you can see that. So initially that PVS goes to maximum power because of that incremental conductance MPPT. So it reach around 7500 watts, and also here you can see the power, right? So this is a load power, AC load power. So it's around 2000 watts, and then so this power is given to the grid by the inverter. So the power is around 1500. So here load is 2000. We are sending only 1500, around 1500 watts. So the remaining power is taken from the grid in order to drive this AC load. So here you can see that the PV power will be it changes from 7500 to nearly 4000 because of periodic changes from 1000 watts per meter square to 500 watts per meter square. So after that, here you can see that the power is changed from 4000 to 0 watts per meter 0 watts because of changing irradiation from 500 watts per meter square to 10 watts per meter square. So because of the here you can see that, right, the battery, right? So battery initially going for charging, and when the battery that PV power comes to 4000 watts, it comes to charging, and PV power is comes to 0, again it going to charge within higher amount of current. Okay. So after you can see the here, right, when the irradiation change from uh, 10 watts per meter to 500, so the PV power is again increasing. So because of that, you can see that discharging current will be decreased. So after 1.2 seconds, the irradiation change to 500 to 1000 watts per meter square. So here you can see that battery goes to charging mode. Okay. So you can see the SOS of the battery. So initially it going for charging, and then goes to discharging, and then goes to discharging, right? So and then it goes to discharging, and then it comes to charging. Okay. So this SOC charging discharging is happened because of based upon the PV power. Okay. So now we can see that this is the grid voltage, inverter current, grid current. So here you can see that here the condition, you can see that the condition of the PV and the SOC is greater than 10 percentage. So in this condition we are sending power to the grid only, that means gridded AC load only. So the contacted current within 3 amps. So here you can see that the peak amplitude of the inverter current is maintained at 3 amps. Okay. So this is the grid voltage, inverter current, and grid current. So here you can see that this is AC voltage, line to line voltage, and then AC load current. Okay. So here you can see that this is a DC bus voltage is maintained around 700, and then current of the DC load. So this is a DC load power. So DC load power maintained around 2500 watts. Okay. So this is working of the system under that means here we are maintaining SOC is 50%. So next I'm going to simulate the same model when the SOC of the battery I'm going to fix at 9%. Okay. So when the battery having 9%, and I'm going to change the irradiation the same concept, that means 1510 and then 500 1000. So here we are going to check the operation of grid inverter. Okay. So again I'm going to simulate this model, and then you have to check the results. So here I'm going to simulate the model. So initially battery goes for charging because it having power to charge, as well as it can able to supply the power to the DC load as well as grid. Okay. So here you can see that it maintain after 3 peak and 2. Okay. And also you can check the power of the DC load is 2000. We are getting power from the PV. The remaining power will be taken from the grid not to balance the DC load. So here now we can see that PV power is reducing because of reduction in the radiation from 1000 to 500. So because of that, battery goes for discharging now in particular condition. Okay. And here you can see DC load power is maintained at 2500 and DC bus voltage maintained at 700 volt. Now we can see here, right, the PV power is goes to 0. That means IPV is less than 0.5. So because of that, what will be happen, right? Here batteries goes for charging more. That means now the condition is IPV is less than 0.5 and the SOC is less than 10 percentage. So we are getting power from the grid. Okay, so because of that, here you can see that uh, grid current changed to 10 amps, right? That means inverter current change to peak current change to 10 amps, and you can see here, right, the power value of the grid. So this is grid power. The grid power around 700, right? So here you can see that. So this is lower power, right? Is 2000. So here you can see that. So inverter power is around minus 5000, right? Sorry, minus 5000. That may now grid supplying the power to the AC load as well as supplying the power to the solar PV system. Okay. So now we are getting the power from the grid to charge the battery, because here battery power is 9% only, and also PV power is around only 7500. So here battery having low power, low SOC. So now to charge the battery here, getting the power from the grid. Okay. So now we have to check the TBST of the grid current. Okay, or inverter current. So for that I'm going to open the FFT analysis and I'm going to use input 2. So I'm going to check the THT during that the power taken from the grid. Okay, so the THT around 1.98 percentage. So I'm going to check the THT during the power sending to the grid. Okay, so I'm going to check the time. So here you can see that THT around only 0.29 percentage. So the THT of the inverter current is less than 5 percentage only. So you follow the IEEE standard. So this is the working of three-phase grid connected solar PV and battery system. Thanks for watching heavy videos. Kindly subscribe channel and also hit bell icon for notification about upcoming videos. Thank you. Thank you so much. Bye bye.